In today's lesson, we'll be doing section 10.1, which is about exponential functions. We'll be determining what an exponential function is and how to graph them. Today's focus will be primarily on graphing. Okay, an exponential function is a function in which the x, or the input, is found within an exponent. Okay, a couple conditions need to apply. Okay, the first condition is it cannot equal 0. If the a value in this function was equal to 0, then it would just be f of x equals 0 and be a horizontal line on the x-axis. Okay. The b value needs to be greater than 0, needs to be positive, and b is not going to equal 1, because if it was 1, okay, then that 1 to whatever power would always be 1. The domain is going to be, in an exponential function, the domain will always be all real numbers, because again, we're going to be inputting into an exponent, and there's no numbers that you cannot input into an exponent. Okay, the range will be all positive real numbers if the a value is positive, and all negative real numbers if the a value is negative. Okay, the x-axis will always be an asymptote. The graphs will always contain the coordinate 0a, input 0 for x, which means anytime 0 is an exponent, you get a value of 1. So it'll be 0a. And then they have two types of functions. We have growth and decay, okay, and they depend on the b function. A growth function is when the b value is greater than 1, and a decay function is when the b value is between 0 and 1. Okay, so if the b value is greater than 1, then it's growth, and if the b value is a number less than 1 between 0 and 1, then it is a decay function. Okay, we're going to graph this function. We're going to go through the steps together. Okay, f of x equals 2 to the x power. First, we want to identify what the a, b values are. In this case, a is 1. I know you don't see it there, but there is a 1 that is multiplying the 2 to the x power, and 2 is your b. 2 is the base on the number that's being raised to the x power. Okay, what do we know from this? Okay, this is all the stuff we know. For 1, the graph will contain the point 0, 1. Okay, that's your 0a. It is a growth function because the v value is greater than 1. Okay, it will move up to the right. Okay. The domain is all real numbers, and the range will be all positive real numbers because the a value is positive. The x-axis will be an asymptote, okay, and we'll make a table that will handle the rest of the values. Okay, so the x-axis will be an asymptote. Now we're going to make a table for that asymptote. Okay. So we have our function here. We're going to input these values into it. Okay, and this is what it looks like. Now, when we say the x-axis is an asymptote, the x-axis is a horizontal asymptote. Okay, so the graph is not going to cross over that black line that I just drew. Okay, as you input -2, you see it's fairly small at 1/4. When you input 1, you get 1/2. When you input 0, okay, you get 0. Now remember, when you input these negatives, this is 2 to the negative second power, which is really 1 over 2 to the second power. That's why we're getting the 1/4. Okay, and you see each other input. Okay, we put these points on the graph. You see it moving up to the right, which is a representation of a growth function. As it goes to the right, it increases in value. We're going to graph this function. What do we know about this function? We have an a value of -1 and a b value of 1/2, which means the domain is all real numbers again. The range will be all negative real numbers because the a value is negative. It contains the point 0, -1. This is a decay function because the v value is between 0 and 1. Okay. It will approach the x-axis as it moves to the right, so it's actually going to decrease as it moves to the right. It's going to start high and go low. Okay, and again, what's not up here that we also know is that the x-axis is a horizontal axis, horizontal asymptote. Excuse me. Okay, again, inputting values in for the variable. Okay, input your negatives. Remember, negative exponent will change to the reciprocal. And this is what our graph is going to look like. Again, the x-axis is a horizontal asymptote. Okay, and this is more representing of a a decay function. The function itself goes closer to the asymptote as we move to the right. Okay. let's see one more together. Actually, you can try get started on a lot of this. Okay, right now we've got 1/2 times 3 to the x power. Decide whether it's growth or decay. Where's the 0a value? Where's the horizontal asymptote? What's the domain and range? Okay, all these things. Okay, you can start working on. Take a moment, pause the video. Okay, after you find these things, did your graph look like this? Again, increasing to the right because this is a growth function. The b-value is higher than 1. Positive, so it should be above the asymptote, okay, above the x-axis. And this is what it should look like. Okay, we want to determine if these are growth or decay, so pause the video, please. Determine if each function is growth or decay. Example number 1 here, b-value is 0.7. This is decay. Okay, the a value is 1, the b value is 0.7, which is between 0 and 1. For example 2, okay, the a value is 10, the b value is 4/3. 4/3 is greater than 1. This is a growth function. Okay, for number 3, the a value is 1/3, the b value is 5, because the b value is greater than 1. This is a growth function. Another thing we'll be doing in this section is simplifying with exponents that we are not quite used to seeing. We have to remember our rules of exponents, especially when they have the same base. When exponents have the same base and you are multiplying it, or when powers have the same base and you are multiplying them together, remember the exponents get added together. Okay, so we're literally adding square root of 2 plus 3 square root of 2, which is 4 square root of 2. What you can do to simplify that is you can take the 3 to the 4th power, which is 81, leaving the square root of 2 as your exponent. Okay, remember when you, for example 2, when you are dividing, okay, remember when you are dividing, you need to take the, you subtract the exponents, excuse me, okay, when they have the same base. So we're using the same base of 5, subtracting 2 square root of 3 minus square root of 3, which is 1 square root of 3, so it's 5 square root of 3. Remember, when it's power to a power, what we do with the exponents is multiply those exponents. So it is 7 square root of 2 times square root of 5 power, which is 7 square root of 10 power. The 4th example here, I want you to follow along with me. Okay, I can't do anything with these until they're the same base. What you need to notice, and again, it's observation, is that these are both 8 and 4 are both powers of 2. So we're rewriting them. 8 is 2 squared, or 2 to the 3rd power. 4 is 2 squared. So really what we have here is 2 to the 3rd power raised to the square root of 6 power. So we have 2 to the 3 squared of 6 power. And when we have this, we have power to power again, 2 squared to the 3. And what I didn't point out is that we simplified square root of 54, okay, to 3 squared of 6. So we have 2 squared raised to the 3 squared of 6 power. Multiply those powers together, and we get 2 to the 6 square root of 6 power. And then now that we have the same base of 2, we get to add the exponents. 3 square root of 6 plus 6 square root of 6 is 9 square root of 6. You could find out what 2 to the 9th power is, and then have that to the square root of 6 as well. Another thing we'll be doing is solving using exponents. What you're going to see today is that we, again, are going to be using same bases. We have 3 to the 2x plus 1 power equal to 81. So what we want to do is get both sides to have the same base. If both sides have the same base, then the exponents need to be equal. Okay. Remember, if we have an equal sign, both sides need to be the same. Work on the bases first. Can we rewrite the bases so that they are the same? In this case, yes. We have the 3 to the 2x plus 1, and 81 can be rewritten as 3 to the 4th. Okay, now that the bases are the same, and we need to solve for when they are equal, the exponents need to be the same. So really it comes down, it's not that the bases cancel out, it comes down to just that the exponents need to be the same. So we set 2x plus 1 equal to 4, solve, and get x equal to 3/2. Same principle here, okay, 4 to the 2x equals 8 to the x minus 1. Okay, if we can get the bases to be the same, then we just need to set the exponents to be the same. And you should notice again that 4 and 8 are powers of 2. 2 squared to the 2x power and 2 to the 3rd to the x minus 1 power. Use your power to power rule, multiply the exponents, so we really have 2 to the 4x power and 2 to the 3x minus 3 power. Now that the bases are the same, it's not that they cancel out, just that the exponents also need to be the same for the equal sign to be true. So we're concentrating on the exponents. So 4x equals 3x minus 3. Solve, you get negative 3. I want you to try these examples for class tomorrow, especially. Okay, I'm going to star these, especially the inequalities. Okay, I know you have not seen an example of an inequality, but I want you to try them on your own, see if your solution makes sense. Okay, and we will go through these 4 in class tomorrow.